Welcome back. In today's lecture, I would like to invite you to join me on a tour through our lab at the IBS Center for Climate Physics. Just to summarize what we found in our last lectures. We saw that weather and large-scale climate phenomena can influence the delta 18O of water vapor and precipitation. We use our supercomputer to better understand how past climate may have affected these phenomena and their impact on global and regional water delta 18O. To understand the relationship between climate and delta 18O of precipitation over Korea, we are collecting water samples as part of our joint KWIN project. What matters for the calcite formation inside the cave is the drip water, which is essentially rainwater that has undergone several processes in the soil and epikarst layers above, such as evaporation, dissolution of limestone and others. To support our KWIN project, our ICCP team is also collecting drip water samples from inside several caves. Eventually, calcite is formed and we measure the delta 18O using our isotope ratio mass spectrometer. Please join me now on our lab tour.
Hi, my name is Nitesh Sinha. I am a postdoctoral research fellow here at the center, ICCP, and my research interest is isotope hydrology and paleoclimatology. So as a part of this, I am in charge of KWIN project, and I will do the isotopic analysis of rain samples. And today I will show you how we do the isotopic analysis of the rain samples, as well as how we do the isotopic analysis of a carbonate sample using mass spectrometer.
In this fridge, we store the KWIN water samples. We extract the water using a small syringe. Then we add a filter onto the syringe to remove pollen, dust and other small particles that could impact our measurements. The largest part of the collected water is stored in extra vials in case we want to conduct more analysis in future. Just a tiny little part of the water that is collected by KWIN will be analyzed in our water isotope analyzer. These are the tiny little vials that go into our water isotope analyzer. Nitesh is just filling them with a pipette. Let's move over to the main instrument that measures the water isotopes. Robot with a syringe automatically loads the samples into the laser cavity ring down system. As the name says, inside this black box is a laser whose wavelength we can tune. This laser shoots light of a specific wavelength into a cavity that has one mirror on each side. A sample of water vapor that we would like to analyze is then injected into this cavity, illuminating the sample. The laser light is trapped in the glass tube, shooting back and forth between the mirrors many times. When we turn off the laser quickly, the intensity of the laser light between the mirrors will eventually decay over time. The decay time depends on the light's absorption properties of the sample inside. It turns out that water vapor based on 16O has slightly different absorption properties compared to water vapor which has 18O. By comparing the decay time of the laser light between the mirrors for different wavelengths, we can then estimate the ratio of lighter H2 16O over H2 18O. A computer program then analyzes the data from the laser system and calculates our desired isotope ratio of oxygen and hydrogen. Over the past months, we analyzed with this method the water samples that participating high schools collected as part of the KWIN project in 2020. We obtained water isotope values from about -2.1 per mil to about -5.7 per mil during the month of May. Then quickly in June and July, when there was a massive rainfall in South Korea and severe flooding, we saw a large drop of the delta 18O values to -8 and up to -14 per mil. Why? Remember that rain gets more and more depleted in 18O, more negative delta 18O values, the longer the pathway is from the source region where the water evaporated and the final rainout location. During the pre-Changma period in May, the main tropical rain band hasn't reached South Korea yet. Rain falling in South Korea during May originated from water vapor that came from the East or West Sea. Therefore, the delta 18O values are not as negative, more in the range of -2 to -5 per mil. Then, once Changma arrives on the Korean peninsula in June and July, the strong southerly flow from the tropical regions brings a lot of tropical moisture from farther away with significantly more negative depleted delta 18O values. Moreover, the fact that there is more rainfall also means that the delta 18O will get even more depleted due to the strong amount effect that we discussed before. These processes explain the relatively strongly negative delta 18O values from all KWIN stations in June and July. The Changma in 2020 was very strong and it caused a lot of flooding in South Korea. This is consistent with the very negative delta 18O values of the summer KWIN water samples. By plotting the 2020 KWIN water isotope measurements along with the ones we collected ourselves here in Busan, the following picture emerges. There is a strong seasonal cycle in delta 18O, which means there is a strong seasonal cycle also of the water vapor pathways. High rainfall in summer, as illustrated by your rainfall amount measurements, is accompanied by very low delta 18O values. Interestingly, we also see large regional differences between the different KWIN sites in Korea, both in terms of the mean monthly rainfall in delta 18O. We will explore those a little bit later once we also have the data available from the 2021 KWIN phase. We are very happy that several more schools joined us for KWIN this year. Welcome again to Gyeongbok Science High School, Chungnam High School, Jeju Jeil High School, Daegu-il Science High School and Osong High School. Thanks a lot for joining our program. We have already analyzed and received your water samples from the last months and will start to share the results with you shortly. Now let's move over to our Speleotherm stable isotope lab. What you see here is a small speleotherm from a cave in China. To extract small calcite samples, we take a microdrill. The speleotherm is quite hard, so it takes quite a while to drill out enough calcite powder. The powder is then filled into a small vial. Afterwards, the sample is weighed on a microbalance. For our isotope ratio mass spectrometer, we only need a tiny amount of calcite. Our main instrument is an isotope ratio mass spectrometer. It has two main components. One is the sample preparation device. In this instrument, the tiny little amount of calcite that we drilled from the stalagmite sample gets dissolved in phosphoric acid. The dissolution of calcite in acid generates CO2. Essentially, two protons in the acid react with the carbonate ion to form CO2 and H2O. If the carbonate ion contained one 18O and two 16O atoms, the 18O can either go into the chemical reaction to the CO2 or to the H2O. This ratio is partly temperature dependent. By setting the temperature in the sample preparation device and by measuring the 18O-16O ratio in CO2, we can then deduce the original 18O-16O ratio of the calcium carbonate sample. The 18O-16O measurements of CO2 are conducted in this second device. The second device is a mass spectrometer which accelerates ions of the sample CO2 gas. As the positively charged ions pass a magnetic field, their path is deflected because of the Lorentz force. For the same level of ionization, heavier ions, for instance C18O-16O, are deflected less compared to the lighter ones. At the end of the instrument is a detector that measures the number of light to heavy ions according to their deflection angle. On the computer, we can then see the final data and control the instrument. Now we know how from the little powdered calcite samples that we extracted from a stalagmite, we can measure the delta 18O and other isotopes. However, to reconstruct climate information from the past, we need to know for each speleotherm calcite layer when the calcite was formed. In other words, we need an age model that allows us to link our delta 18O measurements with a time in the past. This is done through a method called uranium-thorium dating. It is based on other isotopic measurements of the radioactive, naturally occurring isotopes of uranium-238, thorium-234, thorium-232 and thorium-230. Unfortunately, I can't go into the details of this method, and unfortunately, no lab in South Korea can carry out this analysis so far. This is why we have to send a part of the sample for dating to our colleagues in Taiwan, China, or the US. When their data come back, we can then put the delta 18O measurements on a time axis, which means we can really interpret when things changed in the climate system. Let's see what the data tells us. By combining several speleotherm delta 18O data from different caves in South Korea, we can identify the common signal. In this figure, time goes up from 5,000 years ago to about 1,000 years ago. We are seeing long-term shifts in delta 18O, which we can interpret as dry periods, such as from 1200 to 2000 years ago, and wet periods, such as those from 2000 to 2800 years ago. Interestingly, similar patterns can be found in other parts of East Asia, which highlights that these shifts in rainfall were a large-scale phenomenon, related mostly to massive shifts and reorganizations of the East Asian summer monsoon. The wet and dry cycles are not directly related to any known external forcing, such as changes in Earth's orbit, which may take much longer, or to changes in solar activity. This means that the climate system itself, through the interaction between the atmosphere and the oceans, can generate this type of variability. How this works in detail needs to be further explored with our supercomputer climate model simulations. Together with our colleagues from Gangwon National University, we are planning to make a continuous reconstruction of past climate over the Korean Peninsula that extends back to a few 100,000 years using multiple stalagmite samples. Similar efforts have been made in the US, India, China, parts of Northern Africa and in Europe. This would allow us to determine the drivers of past climate change in the East Asian monsoon region. The paleoclimate data will then be compared with our supercomputer simulations covering the same period. If we find a good correspondence between computer model and reality, we can also be more confident in the computer models that simulate the climate response to increasing future CO2 concentrations, global warming. In other words, we can use paleoclimate data to improve our future projections of global warming. We see that paleoclimate isotope data are an incredibly powerful tool. They tell us something about what happened, why something happened, and they provide a means to calibrate and benchmark our computer model simulations. This concludes my fourth lecture. Our lectures covered a wide range of subjects, from isotope physics to ice ages, from atmospheric dynamics to the geology of caves. I hope very much that whenever you encounter water in your daily lives, taking a swim in the ocean, slurping your mother's favorite kalbi tongue, doing the laundry or taking a shower, that you will remember one thing. Water is not just water. Water comes in various forms, which you can't see or taste. The different types of water only differ by having 1 or 2 neutrons more in the oxygen or hydrogen atoms. By measuring their relative abundances, we can learn something about the hydrological cycle, rainfall, the atmosphere, and past climates. Thank you all for attending and for your enthusiasm in contributing to the study of the water cycle over South Korea and by participating in our citizen science project KWIN. The KWIN data from your school will be collected on our web pages and the NAVA blog page that we have established. We will keep you updated on any exciting developments, discoveries. At the same time, we would like to encourage you to read more about this fascinating subject. Ask questions to our participating ICCP scientists and reach out to the other high schools who are participating in KWIN. Have a wonderful summer.